Welcome back to another calculus lesson. This is Mr. Thompson. We're looking at section 2-4, continuity and discontinuity. Well, pretty much looking at the difference between the two from pages 45 to 49. Now, first off, when you look at a series of continuous and discontinuous situations so that we can identify them better. Now, we've already looked at some good examples. If we have a function that looks like this is a removable discontinuity. Well, if it's discontinuous, it means it is not continuous. So it's a removable discontinuity. If we have a situation, almost the same thing, but at that spot, there's another dot somewhere else, well, it's just the same thing again. It's still a removable discontinuity, which is not continuous. Another example we've looked at is where instead of continuing from the open circle, it starts again somewhere else and then keeps on going. This is not a removable discontinuity. This is what is called a step discontinuity, which is once again discontinuous. It is not continuous. Another example we looked at in a previous problem set is something like this. We have a graph that shoots up and then comes back down, basically having a vertical asymptote. This is an infinite discontinuity. And it is discontinuous. So all these four examples are situations where we have a discontinuity. So let's look at examples where we have continuity, where it is continuous. Well, an easy example is a line. There's no breaks, there's no gaps, there's no open circles, nothing. This would be straight up continuous. Now, a special situation where we have something like this. This is continuous, but it has some problems with it. This little pointy part is something called a cusp, and I'll define those here in a second. But this is still a continuous function, and actually it would be a series of functions. So these two examples are examples of continuity. These four examples are examples of discontinuity. We got to be able to identify which is which. Now, let's talk about what continuity and discontinuity even is. So, continuity is defined in the book. Now, it gives a mathematical definition, so it's a little hard to read, but it says function f is continuous at x equals c if and only if three things are satisfied. F of c exists. Now, by exists, we mean it's not infinite, it's not indeterminate, something along those lines. It exists. 2. Limit, as x approaches c, of f of x exists as well. And 3, that limit that I just mentioned is the same thing as plugging in c. If these three things are satisfied, then it is continuous at that point. Now, functions can be continuous in one spot and not continuous in others. So that's something we'll deal with later. But continuity means these three things are satisfied. Now, discontinuity is the opposite. At least one of these things is not satisfied. But we don't need to define that. We just define continuity, and discontinuity is the opposite. Now, we can also talk about, instead of a point, an interval, which means a series of points from an A to a B, so to speak. These still have to apply for that interval at all points on the interval. Now, it also gives us the definition of a cusp. Now, a cusp is a point on the graph at which the function is continuous, but the derivative is discontinuous. Now, remember, derivative is the instantaneous rate or slope. Okay, so in our example from here, this is a cusp because on that point, the rate is discontinuous because a fraction of a second ago it was shooting up and now it's shooting down. It's an instantaneous change in the rate. That doesn't work. That's like driving one direction, then the next instant, a 1/1000th of a second later, you're driving the other direction at the same speed. Okay, that does not work. It doesn't work like that. So it's discontinuous. Now, the function is continuous, but the slope, the rate, the instantaneous rate, is discontinuous. So I'm going to say f of x is continuous. However, the derivative, which is written as f apostrophe x, is discontinuous. Now, this little apostrophe means derivative. We're going to see that function notation quite a bit. These are our definitions, continuity and cusp. Pretty simple. Now, one more thing we got to look at before we look at some problems is the idea of one-sided limits. This solves some issues that we had started seeing in the last couple lessons. So one-sided limits. Now, one-sided limits means you can approach it from either side of the point. So let's say we have our point C. Well, if we have the limit as x approaches C of f of x, that is not a one-sided limit. What changes it to one-sided is a small plus or minus. This means it's coming from the positive side. So this means from the right side. The limit as x approaches C minus f of x means it is coming from the left side. Now these are different, and we're going to look at some examples where this applies. However, looking at limits this way will solve some issues that we started having. So let's go ahead and look at an example. Example 1, directly under where it talks about one-sided limits. So we have example 1 from page 48. Now it uses the following functions. F of x equals, and we have three functions in a bracket. X plus 4 when x is less than or equal to 2. Negative x squared plus 8x minus 8. From 2 to x to 5. And x plus 2 when x is greater than or equal to 5. Now, it gives us a pretty interesting graph. Up until 2, it's just straight line, ending at a closed dot. However, it starts again, and then it goes up to 5 in a downward parabola, and then it shoots up again. Now, this has a step discontinuity and a cusp. Okay, so I'm going to fill those in. This is the cusp, and this is the step discontinuity. Now, we have the function graphed, so I'm not going to go ahead and graph on the grapher right now, which would be part A. Part B, does f of x have a limit as x approaches 2? No. We looked at that before. Step discontinuity says we do not have a limit as x approaches 2. And it is also not continuous at 2. However, I'm going to go a little bit above and beyond on example 1 and say that it actually does have a left and a right limit. So, limit of f of x as x approaches 2 from the left. As it approaches 2 from the left, You see it's right here. And if we look in the book, that's at 6. So it equals 6. However, the limit of f of x as x approaches 2 from the right is different because it's this spot, which in the book says it's at 5. So notice, from the left and the right, you can have entirely different limits. So we have 5 and we have 6. Actually, I think the book puts it at 4, but that's alright. I'll go ahead and put it at 4. So I follow exactly what the book said. We'll say 4. Now, same kind of question for does f of x have a limit as x approaches 5? 1, 2, 3, 4, 5. Here, yes it does. A cusp is continuous, has a limit. Limit as f of x approaches 5 equals, well, if we go over to 5, hop over, it looks like it's at 7. So I'm going to go ahead and say equals 7. Now, if I wanted to look at the left and the right, we're going to notice something. Limit as f of x approaches 5 from the left, it's at 7. Well, the limit as x approaches 5 from the right of f of x is the same spot, 7. So the cusp is in the same spot, so our limit is the same thing as the left and the right limits. So the one-sided limits in this kind of case are equal to the main limit. That is a special case. In a step discontinuity, it's not. In a cusp, it is. There's other situations where it may or may not be true as well. So let's go ahead and look at some problems out of the problem set for this section.